Hello, my dear students. Today I will be discussing about the failure of dams and criteria for structural stability, or also it is called as modes of failure. The following are the modes of failure of a dam. The first one is overturning, the second one is sliding, third one is compression or crushing, and the last one is tension. Let us discuss about the overturning failure. If the resultant of all the forces acting on a dam at any of the section passes outside the toe, the dam shall rotate and overturn about the toe. The overturning of the dam section takes place when the resultant force at any section cuts the base of the dam downstream of the toe. In that case, the resultant moment at the toe becomes clockwise. On the other hand, if the resultant cuts the base within the body of the dam, there will be no overturning. A dam fails in overturning when the total horizontal forces acting on the dam section are quite great in comparison with total vertical forces. For stability requirements, the dam must be safe against overturning. The factor of safety against overturning is defined as the ratio of righting moment to the overturning moment, or it is also called as resisting moments divided by overturning moment, or summation of mr divided by summation of m naught. The value generally varies between 2 to 3. If the resultant of all the possible forces, internal as well as external, acting on the dam cuts the base of the dam downstream of the toe, then dam would overturn unless it can resist tensile stresses. To safeguard the dam against overturning, the resultant of the forces should never be allowed to go downstream of the toe. If resultant is maintained within the body of the dam, there will be no overturning. All the forces acting on the dam cause moments. Some of the forces help to maintain stability of the dam, while others try to disturb the stability. The moments of the forces helping dam to maintain its stability are known as resisting moments, MR. The moments of the forces that try to disturb the stability of the dam are known as overturning moments, M0. As soon as M0 exceeds MR, overturn of the dam would take place. The value of factor of safety against overturning should not be less than 1.5. Since the magnitude and direction of each and every force considered in the previous articles are known, their moments about to the toe can very easily be found out, and factor of safety can be calculated. So this is about the overturning. Let us discuss about sliding failure. In this mode of failure, the dam fails in sliding. A dam will fail in sliding at its base or at any other level if the horizontal forces causing sliding are more than the resistance available to it that level. It may be takes place on the horizontal joint above formation on the foundation. The resistance against sliding may be due to friction alone or due to friction and shear strength of the joint also. Shear strength develops at the base if benched foundation is provided, and at other joints if the joints are carefully laid so that a good bond develops. Shear strength also comes into play because of the interlocking of the stone in a masonry dams. Sliding will occur when the net horizontal force exceeds the frictional resistance developed at that level. And also, this failure occurs when the horizontal forces causing sliding are more than the resistance available to it at that level. If the shear strength is not taken into account, the factor of safety is known as factor of safety against sliding. The factor of safety against sliding is defined as the ratio of actual coefficient of static friction on the horizontal joint to the sliding friction. The sliding factor is the minimum coefficient of friction required to prevent sliding. If summation H is the sum of horizontal forces causing the sliding and summation V is the net vertical forces, the sliding factor tan theta is given by shear force safety factor is equal to tan theta. It is not safety factor, sliding factor is equal to tan theta, that is equal to sigma H divided by sigma V. And factor of safety against sliding is obtained by factor of safety is equal to mu divided by tan theta. So that is equal to mu into tan theta is sigma H divided by sigma V. So mu into sigma V divided by sigma H. The value of coefficient of friction mu varies from 0.65 to 0.75. The factor of safety against sliding should be greater than 1. It is considered that a low gravity dam should be safe against sliding considering friction alone. However, in large dams, shear strength of the joint should also be considered for an economical design. The factor of safety in that case is commonly known as shear friction factor and is defined by the equation mu into summation of V plus A into C divided by sigma H, that is equal to mu into summation of V plus BC divided by sigma H, where C is average cohesion or shear strength of the joint, the value of which varies from 1300 kilonewton per meter square to 4500 kilonewton per meter square for good rock and 650 to 1300 kilonewton per meter square for concrete. B is width of joint or section. A is area of the joint, that is equal to B into 1 for unit length of dam. This is about the sliding. Next one is compression or crushing failure. If the compressive stress developed anywhere in the dam exceeds the safe permissible limit, the dam may fail by crushing of the dam itself or of foundation. The maximum compressive stress can develop at toe when the reservoir is full of water. If reservoir is empty, the maximum compressive stress is likely to develop at the heel of the dam. The magnitude of maximum compressive and minimum compressive stresses can be found out by using the following equation. That is, Pn is equal to V divided by B into 1 plus or minus 6E divided by B. Can see this figure. Okay, there are three diagrams. A, B, C. Here in this equation, Pn is equal to value normal stress, V is total vertical force, B is width of the dam base at level of consideration, E is eccentricity of resultant force R from the center of the base, and H is total horizontal force and R is resultant force. Plus sign is used to evaluate the amount of maximum compressive stress which will occur at toe of the dam when reservoir is full, and minus sign is used to evaluate the amount of minimum compressive stress which will occur at heel when reservoir is empty. Figure A shows normal stress distribution for a general case when the pressure at both toe and heel are compressive. This one, okay. Next is figure B shows the maximum compressive stress occurs at the toe, and for safety this should not be greater than the allowable compressive stress for the foundation material. Figure C shows the pressure distribution at the heel. Okay, here this is for the general case, and this is for the toe, and this is pressure distribution diagram for the heel. Next one is tension failure. Both cement, concrete and masonry are very weak in tension. Hence, from safety point of view, the tension is not allowed to be developed in the dam anywhere. If eccentricity E greater than B divided by 6, then tension will be developed at the heel of the dam. Since concrete cannot resist tension, no tension is permitted at any point of the dam under any circumstances. As soon as E exceeds 6B, tension is developed in the dam and dam face by opening of the joints, as concrete and masonry are almost nil in tension. When reservoir is full of water, tension is likely to develop at heel, and when reservoir is empty, tension is likely to develop at toe of the dam. In other words, it can be stated that until resultant of the forces lies within the middle third width of the base, tension cannot develop anywhere in the dam. In the case of gravity dams having moderate height, no tension is allowed to be developed anywhere. However, in case of very high dams, a small tensile stress may be permitted to be developed, but only for short durations during heavy floods or earthquakes. It is not having heavy floods. Once tensile cracks developed at heel, the dam cannot be rendered safe. Due to tension cracks, uplift pressure gets increased and consequently net vertical downward force is reduced. This causes further shifting of the resultant towards the toe, and this leads to further lengthening of the cracks. Due to lengthening of the cracks, effective width of the base is further reduced and compressive stress at toe further increases. Ultimately, compressive stress at toe increases to such an extent that dam fails by crushing at toe. Here in this figure you can see the effect of tension cracks. Tension crack is developed here. Okay, this is the A corresponding to R1 modified uplift pressure diagram. This is the original uplift pressure diagram. Let us see what are the precautions can be taken against the dam failure. The first one is to prevent overturning. The resultant of all forces acting on the dam should remain within the middle third of the base width of the dam. In the dam, the sliding should be fully resisted. When the condition for no sliding exists in the dam section, in the dam section, the compressive stresses of concrete or masonry should not exceed the permissible working stress to avoid failure due to crushing. There should be no tension in the dam section to avoid the formation of cracks. The factor of safety should be maintained between 4 to 5. Okay, so these are so now I have discussed some of the modes of failures of the dam, overturning, sliding, crushing or compression and tension. I hope all of you understood. Thank you.